In this video, I'm going to look at the same example as the previous one, but with a different explanation for the solution. Okay, so the differential equation that we've got here, we know is a Bernoulli differential equation because you've got your dependent variables in two different places here, and you've got one of them being y to the power 3, which is neither 0 nor 1. Okay, so in this case, if you look at the general form for Bernoulli differential equation, your n value here is going to be 3. Okay, so what I want to do is I want to take this Bernoulli differential equation and change it into your linear form. Before we even get to do that, we however have to change it into the Bernoulli standard form first, which means your first term where the derivative is, the value in front of that derivative has to be 1. So then we have to divide through by your x value. So that means you'll have dy dx 2 over x times y equals x to the 6 y cubed. So there you've got Bernoulli standard form. Okay, so in this case, p is going to be 2 over x. Your q is going to be x 6. Once I've got that, I want to convert this form into linear form because then it's easier to solve. You can just use the linear method to solve it. So if you look at the linear standard form and you look at your value on your right hand side, you will see that you don't have your dependent variable on your right hand side at all in the linear form, which means, for our example, you don't want to have that y cubed there. So I am going to divide through by y cubed, which means I'm going to get y to the minus 3 dy dx 2 over x, y to the minus 3 times y equals x 6. Okay, if I simplify, dy dx, that becomes y to the minus 2 equals x to the 6. Right, so we've sorted out the right-hand side of the equation. There is no dependent variable there, which means that that term is the same as the term in the standard form for the linear differential equation. If we go to the next part, that part there, right, we want to convert that into the same form as linear, which means that the dependent variable you want to have to the power 1, not minus 2. And the way we're going to do that is we're going to say let z equals to y to the minus 2, which means your equation is going to be converted to this times z equals x to the 6. So this term here is the same as that term there, right? Because your z is going to be to the power 1 and you've got y to the power 1 in your standard form. Okay, as we said in the previous video, your first term you also want to convert into linear form, which means that the dependent variable in the derivative has to match up with the linear dependent variable here. Right? Which means your first term has to have a dz dx in it, not a dy. Okay, and we can find out what dz dx is because we know what we've assumed z to be. So we can say from z equals y to the minus 2, your dz dx is going to be the derivative, so you can use the power rule. You take your power, multiply it with whatever is in front, in this case 1, minus 2 minus 1. Because y itself is a dependent of your x value, you add on dy dx. Right? So that is going to simplify to minus 2y to the minus 3 dy dx. Okay? And if we look at your first term here and the derivative dz dx, the only difference you have is that you've got a minus 2 there, but you don't have a minus 2 there. But we can introduce it because it's a constant value. So, if we call that 1, we can say 1 multiplied by minus 2, right, will be minus 2y to the minus 3 dy dx, 2 over x times minus 2 z equals minus 2x to the 6. And if I simplify, minus 4 over x z equals minus 2x to the 6. Right? There we go. And that first term is now just dz dx. So dz dx minus 4 over x times z equals minus 2x to the 6. So this whole term is equal to your derivative of z with respect to x. So that is now in linear form. Once it's in this linear form, we can use the linear method in order to solve that differential equation. Now remember, solving the differential equation means that you are going to find some solution. Z is equal to something. Okay? So that, the linear part, that is where we want to get to. So using the linear method now, you remember that we have to find the integrating factor. So f is going to be e to the integral minus 4 over x. Right? Dx, which means it's going to be e to the minus 4 ln x, which means you're going to have e to the ln x minus 4. Log law says that that is just going to be x to the minus 4, which is 1 over x to the 4. Right? Log laws and your exponential laws. Once you have your integrating factor, you can find the solution for the linear differential equation. Now you'll remember in our previous examples when we did linear differential equations, we used this formula here. Right? And we had the y there. In this case, your dependent variable is not the y. In this case, it's going to be z. So we're going to use a formula that looks like this. Okay? So z stays, your f is 1 over x to the 4, 1 over x to the 4, and in this case, your q value is going to be minus 2x to the 6. X to the 6 dx. Okay, so then we've got z over x to the 4. If we simplify, you're going to have minus 2x squared dx. Right? Z over x to the 4, and the integral of that is going to be minus 2 over 3 x cubed plus your constant value. Okay, so this is going to be the solution to the linear differential equation. So it's going to be the solution to this equation here. But that's not what we want. We want the solution to your original differential equation, which is in terms of y. So your answer has to be with a y in it. But we know what z is. So we can say, but z we found to be y to the minus 2. Which means you're going to have 1 over y squared over x to the 4. And that will be the solution for your differential equation. if you now have initial conditions, you will be able to find your value for C, which means you'd be able to find your particular solution from that.